Hello students, in this video we'll discuss Hadamard's formula for the radius of convergence of Taylor series where the input variable is a complex valued expression. So let's consider for z and z, an expression looks like this. The sum n goes from 0 to infinity of some numbers a n z minus c to the power n. For complex numbers a n and c, the center c is in c, and z is in C. Okay, so in other words, these are complex Taylor series, complex valued Taylor series. Okay, and so what we're going to ask is we're going to figure out when this series converges. So the question, when does this series converge? And of course, we have a notion of convergence because I know what it means for a sequence of complex numbers to be Cauchy, right? So in other words, if the partial sums of this expression are from a Cauchy sequence, then we'll say it converges, just like we did for a function of a real variable in real analysis or in Calc 2. Okay, so when does this series converge, right? And so the answer is we're going to look at this formula. We're going to consider this formula. 1 over r is the lim sup as n tends to infinity of the modulus of these numbers a n to the 1 over n. Will yield a number. This quantity over here could be 0, not infinity, or a finite number, finite positive number, right? So this number r over here is between 0 and positive infinity, right? The cases when r is equal to 0 and r is equal to positive infinity are easy to deal with, right? If r is equal to 0 over here, then this lim sup over here is going to what? Going to infinity, which means the terms are growing faster than any power of n, basically, right? So in other words, that'd be a problem for us, right? If r is infinity, this lim sup is 0, and then the terms in the series are going to 0 extremely fast, right? They're faster than these powers of n, right? So that gives us a hint that you might have no convergence over here and a lot of convergence over here. So we're going to restrict ourselves to the case when r is finite, right? So this formula over here is called the Hadamard formula for the radius of convergence. So this is our Hadamard formula. For the radius of convergence. Excellent. And so what's the proposition we have about this formula over here? So I'm going to assume for us, we're going to assume that r, let's make some initial assumptions. We're going to assume that r is finite. We'll do the r finite case. The case when r is not finite is very easy to do. When r is finite and the center is 0 and c is equal to 0. Okay? Good. And so here's a proposition. Part A of this proposition says that if modulus of z is strictly less than r, then our series over here, let's call it star, then star converges absolutely. B. And remember the absolutely convergence here. What do you know about absolutely convergence series? If a series converges, it may not converge absolutely, but if it converges absolutely, then it has to converge, right? And then part B of this theorem says what? It says that if modulus of z is less than or equal to a number little r, and that number little r is less than big R, then star converges uniformly. Converges uniformly. Beautiful. And the last part of this proposition is what? Is that C says that if you're bigger than R, then the series diverges, then star diverges. Now remember that modulus of z less than r is a circle, an open circle of radius r, an open disk of radius r. This is what? That's the complement of an open disk, right? So I'm not telling you anything about what happens when modulus of z is equal to r, right? That's very similar to the case when you did Taylor series in Calc 2, when you have to worry about the endpoints, right? Now I have to worry about the endpoints of this disk, basically what is essentially a circle, right, of radius r. Good. And so what we want to do is we want to think of the picture in the back of our mind. So here's the picture we're going to look with. So here's our configuration over here. Here's our value r. So here's a circle centered at the origin of radius r. So what we're going to do, of course, in the context of this problem, if modulus of z is less than r, you're somewhere in this disk over here, right? Which means that you're also in some other smaller disk over here. So I'm going to draw a smaller disk, right? And let's say that this blue circle over here has radius little r. And then let's call that, actually I'm going to call that rho. I'm going to make an intermediate thing, and then I'm going to do a little r next, right? And so then I'm going to draw an even smaller circle. and that is going to be little r, right? So in other words, we're going to have this, in our problem, we're going to have r less, at least over here in this situation over here, we're going to have r less than rho less than r capital. That's the situation we're going to think of for these circles over here. And so we have different disks, right? These are all different disks. And so let's prove part A. So here's the proof of part A. Okay. If n is sufficiently large, what do we know? Well, in this case, I know that's 1 over r. So what will happen with the reciprocals of these things? 1 over little r is going to be bigger than 1 over little rho. It's going to be bigger than 1 over r capital, right? So I know that 1 over r is the lim sup of this sequence, and 1 over r is strictly less than 1 over little r. So for n sufficiently large, we have what? We have modulus an to the power 1 over n. For n large enough is definitely bigger than what? Or less than in this case. It's going to be less than these things. It's the lim sup, so it's going to be less than. That's getting closer to the lim sup, so it's eventually going to be less than 1 over r, right? Less than 1 over little r, which says that modulus of an in this case is strictly less than r to the negative n, right? Good. And then what does the tail of our series look like? Then the tail of our series, the tail of star, what can we estimate the terms by? Satisfy the terms in the tail of star. Satisfy modulus an modulus z to the power n. What do these terms look like in absolute value or modulus? In modulus, they look like what? Less than or equal to modulus z over r to the what? To the power n. Now, modulus of z, if z is less, if in this regime over here, what can we assume? Z is going to be less than, if you're inside this disk, then you're going to be less than some r, right? In other words, we're assuming here, so we can choose from the outset, we're going to assume that modulus of z is less than r capital, right? So in other words, in the first part of this problem, if you're less than r, you're definitely less than some little r for some little r smaller than big R, right? I can always squeeze this by the fact that this is an open disk, right? I can squeeze a little tinier open set in there. That's sort of, in some sense, one of the special properties of these topological spaces for these metric spaces, that there's a lot of extra, more open sets you can squeeze in, right? And so now, of course, if modulus of z is less than r, then modulus of z over r, this number over here is less than 1, right? So in other words, this number over here, so modulus of z over r is less than 1. And we've bounded our terms by a convergence series. So our terms are bounded, the tail is bounded by a convergence series, is bounded by a convergence series. If you're bounded by a convergence series, then you converge by comparison, right? So that proves part A. That's proof A. What about B? And so now for B, what we're going to do is the following. We're going to assume now that our modulus of z is less than or equal to little r. And now little r is actually less than rho, and rho is less than r capital over here, right? So now we can run the same arguments. So then modulus an to the 1 over n is less than 1 over r. Okay? And 1 over r is going to be less than what? That's good, right? And in particular, it's going to be less than what? It's going to be, I can make it less than 1 over rho, right? 1 over rho if I want. Okay? Good. By the same argument as before, right? Because 1 over rho is what? Bigger than 1 over r. And so now what can we say? So now let's look at our terms. an z to the n less than or equal to what? Well, n is less than 1 over rho to the n, so this is a rho to the negative n times what? Rho to the negative n times z to the n, but z to the n is less than or equal to r to the n, right? So this is going to be r over rho. Now r over rho is what? R over rho is less than 1 to the power n. R over rho less than 1. And so now what do we have over here? So now we have it bounded by a what? A function which is not dependent on what anymore? This doesn't depend on z. Which is exactly what we need for uniform convergence, right? Good. And so now what's the idea? The idea is now I can apply the Weierstrass M-test because I have our terms in our series are bounded by what? The terms of the convergence series, we're going to apply a Weierstrass M-test. So our series, star, converges uniformly by the Weierstrass M-test. Which we've proven in a previous video. Okay. Then part C is also fairly straightforward, right? So how do we prove part C? Part C, well, for n bigger than or equal to n capital, right? What do we know? Well, let's do this first actually, so let's not say that yet. If modulus of z is bigger than r, this implies that modulus of z is bigger than or equal to some r tilde, right? Which is bigger than r. I can squeeze it in the other way now, right? And then what can we say over here? Now the terms are, now we're in real trouble, right? Because now if n is bigger than or equal to n, I can say that an to the 1 over n is bigger than or equal to what? Is strictly bigger than. Now the reciprocals of these things, the reciprocal of r tilde is what? The reciprocal of r tilde is less than 1 over r, right? So 1 over r tilde is less than 1 over r, right? So these terms are bigger than or equal to what? Bigger than or equal to 1 over r tilde, right? And so that says that an is bigger than or equal to 1 over r tilde to the power n, okay? And so in particular what this says is, this says what? This says that an times z to the n is bigger than or equal to what? Well, zn is bigger than or equal to r, right? So this is going to be bigger than or equal to r over r tilde, right? Good. Bigger than or equal to modulus of z to the power n over r tilde to the n, okay? And now modulus of z is bigger than modulus of r tilde, so z over z tilde in total size is bigger than 1, right? So this number over here, modulus of z over r tilde, is bigger than 1, and I've bounded the terms in our series from below by a divergent series. So that proves our series diverges. The series diverges, hence our series diverges. Now this is great because now I know for a fact that what I get when I give you when I give you a complex valued function, I would just jump the gun and I said, when I give you a holomorphic function, then you have this series. Now the point is that if I give you this series, I have no reason to believe a priori that this is a holomorphic function, because holomorphic function means that the derivative exists, right? All I've shown you over here is that if this r exists and is finite, then you know that you're going to converge uniformly to at least a continuous function, right? But I don't know the derivative exists, right? So what we have to do in the next video is we have to show that when you have an expression like this on the disk of convergence, right, which is a simply connected region, that function will define a holomorphic function, i.e. its derivative exists, and then once this derivative exists on this set, that proves that the function is holomorphic. So we'll show that, that if you have an expansion like this, then your function is automatically holomorphic. Thank you very much.